Hello guys, welcome to Deep Codes, and in today's video we will discuss LeetCode question 211 that says design, add and search word data structure. So you have to design a data structure that supports two functionalities. One is adding words and second is searching for words. Okay. Now the only twist here is, so whenever you encounter some dots while searching a word in a search word function, so whenever you encounter a dot, that means you have to match any letter. So with the help of dot you can match any letter from A to Z. So this question is easy to understand that simply you are doing two things at a time. So firstly you will initialize the class word dictionary, then you will add some words. Let's say you have added bad, dad, mad, pad. So these are the four words that you have added initially. So now that is one functionality for the search. So you search a word and you passed in the search bad. So whenever you search, whenever you call a function for the search, you have to return some boolean value like true or false. So for bad, okay, so here we are searching for pad. So when you are search for this pad, you will return false because we have only three words like bad, dad and mad in the dictionary. Okay, then you search for another word with this string bad. So we return true because we already have bad added in our dictionary. Then we search again, call the search function with .ad for .ad string. So now the .ad means, so for dot you can match any character from A to Z. So you can match for AAD, BAD, CAD, DAD, EAD for any character. So whenever you encounter a dot, any character can be matched. And after dot, the second and the third character has to be A and D. So yeah, that is one word BAD where second and third character matches, DAD where second and third character matches, and MAD where second and third character matches with this. So yeah, we return true because there are multiple words that matches with this word. Now if you search for this word, here we are also searching again for B dot dot. That means the first character has to be B and the second two character can be any. So do we have any word starting with a B? So yeah, there is one word which that is starting with a B. So yeah, we return true for this. So yeah, I hope you guys understood the question logic that what we are trying to do. The question is simple. Whenever we simply add some of the words to our dictionary, we search the words, and while searching we have some additional functionality that whenever we encounter a dot, we can match any character with that dot. Okay, simple. So yeah, and the number of calls for the add word and search function can be large. That is 10 to the power 4. So we have to maintain this. We have to take a look for the time complexity when we are adding a word or searching for a word. Okay. So here guys, the number of add and search functionality or function call at our maximum can be 10 to the power 4. Okay. Now let's say there are 10 to the power 4 words, and each time let's say one time you call for search functionality, or each time you call for search functionality. So maximum this can be 10 to the power 4 into 10 to the power 4. So maximum time complexity can be 10 to the power 8, for which you can write a code. Okay. So this can be maximum time complexity that can be allowed, because anything greater than equal to 10 to the power 9 will give you TLE. Not equal to, greater than 10 to the power 9 will give you time limit exceeded. So yeah, we have to write some code. So what does this mean? So this means that adding a functionality must take big O of n time complexity, and searching a functionality should also take big O of n. Like this is the maximum time complexity, right? This is the maximum time complexity for addition of word and searching of word that should take, where n is what? N is simply the total words present or already stored. So this can be the maximum time complexity that for which we have to code, because beyond this you will get time limit exceeded. Okay. So yeah, there is only one data structure that searches for a word in a time complexity of big O of n, and that is none other than try. So you are required to have some prerequisite knowledge for this try data structure, or this is prefix stream. You can also name it as prefix stream. So here so this data structure is specifically made when you have to add some words, search for a words, or search for prefix. So if you have some kind of functionality to implement in your question, so yeah, the try is only the data structure that provides you with this functionality. So before moving forward to this question, you are required to have some basic understanding of the try data structure, then only you can move forward. And also I have made video on this try data structure 2 days back, because that this question, the implementation of try data structure was a part of LeetCode daily challenge 2 days back. So yeah, I will link the video for this implementation of this try in the description, so make sure you check it out if you have difficulties in understanding try. Okay, now from this point I assume that you have some basic understanding of try data structure. So the only thing that is different here from the try is the search. So in search, what we have something like dot dot cd, c dot dot d. So we have to handle this dot that is not done in a fundamental try data structure. So let me take one example to show you that how we will handle this dot in our try data structure. So let's say you have a function calls like add, search, add, search. Okay, so let's say initially you add ijk, you search for j dot j dot, then you add for abc, abd, abced, then you search for let's say ab dot, you search for ab dot d. So let me take here abddd. Okay, so these are some of the add and search functionality that we have to implement. So yeah, now let me draw the try data structure. So here first initially I take the root node. Okay, now adding the first one. So we add I, then j to the children of I, then k to the children of j, and we mark this as the end of the word. Okay, now we have to search for dot j dot. So what does this dot mean? Dot means that we can match any character. Okay, so whenever you get something like dot here, so initially what we are starting from searching from the root. So whenever we get a dot here, we will search for all the children of the root. See how many children a node can have in a try. A node can have 26 children, because 26 are all the characters from A to Z. So a node can have 26 children in a try. So that means whenever we encounter dot, we have to check for 26 children that are not null. See, in the 26 children, or some are null, and other have function, other have this node present, other have nodes. So let's say for this root node from A to I are null, I is not null, and beyond I is null here. So only from A to Z except I, all are null here, all are null. So we will check for the children that is not null. So here I is not null. Okay, I is not null. Then we go towards the depth. We go from I, then we check for the children of I. Do we have j here? Do we have j as a children of I? That is not null. So yeah, we have j. Then for further again, we check for all the children of I that are not null. So there is only one children of j that is not null, that is k, and we check is k and. So yeah, we can see that k is the end of the word, and so for this we return true. Okay, then we add one word abc. A children, b to the children of a, c to the children of b. This is the end of the word. Then we add abddd. So ab d d d. Okay, then we add abced. A b c e d, and yeah, both these d are end of the word. Okay, now we have to search for ab dot. So let's say ab dot. So first letter is a. So do we have any children of root with a character m? So yeah, this is the children, this is the child of root with a character m. Then we check in the child of a, do we have b? Yeah, we have b. Then we check if in the child of b, do we have one character, only one character, and that must be end of the word. So yeah, this is one character and that is the end of the word, so we return true. So we return true for this. Now if you have to search for something like this, a b dot dot, that means after b you have to match two characters and then it should be end of the word. So let's say a is match, b is match, then c is match, then there is nothing in the c. So we will check for another children of b. So this is second child of b. So one character is match, the second character is match. Now there are only two characters to match after b. Two characters are matched. But do you reach end of the word? No. Then you again check for another child of b. You check one character, you check another character. So two characters are matched. Then you will check, does E is the end of the word? No, this is not the end of the word. So if you have something like this, AB dot dot, and that is not the end of the words, and in this case you will simply return false. Okay, got this? So the last character you have to simply return false if the last character is not the end of the word. Okay, now if you have something like this, AB dot dot D, so A is match, B is match, then you will check for here C, one dot, then after C there is nothing, but here you have one dot and character D. So here you return false and you check for another child of B. See, whenever you have encountered a dot, you after B, so after B there is a dot, so that means you have to check for all the children of B that are not null. So one children you check, you didn't got the answer, then you check, switch to another children of B and such. So this dot is matched with D, yeah, then again dot, so this D is matched with this D, then there is a D. Okay, this D and this last D are matched, and after this there is nothing, so we have to check, is D an end of the word? Yeah, it is the end of the word, so for this we will return true. Okay, so the same type of search that we do in a try data structure we will do here. The only thing is, whenever you encounter a dot, then you will check for all children of parent. Check for all the children of parent. So initially, let's say A, so in this case, let's say you are searching for A. So in a root, you will only directly check for if the character A is null or not. So if there is, but instead of if there is dot, then you will check for all the children of root. Simple, got it? So yeah, this is the only difference that we have from the try data structure, that when you encounter a dot, you have to check for all the children of the parent. So let us now take a look at the code. The code is simple. The simple implementation of try data structure. See, this is the try block where we have one parameter for each end of word to check if the word, if it is the end of the word at the node, and for each node has 26 children. Got it? So yeah, for each node we will create the set 26 children. We will initialize them with a null pointer. So in the starting of this word dictionary, whenever we initialize word dictionary, we will also take the instance of this try node root. So we are just creating the instance of this try node. Then add functionality is simple. We have to add a word. So first we will check, do we have any children that is equal to null pointer. So this is same as try node. So whenever we have a null pointer, we create a new node, and else we simply move to the node. So this is the same addition of word in the try functionality. Now the only difference will come here in the search functionality. So in a search functionality, what we used to do. Okay, so let me also show you the search functionality for searching a word in a try. So guys, here side by side I have pasted the search functionality of this try, and this is for the current function. So here we simply call the search helper. So what does this search helper does is, as we discussed, the search helper will whenever we encounter any dot, we will check for all the children of the current node, that is not equal to null. Okay, so see, in the basic try, what we used to do, we used to check if the character of the word is is equal to null. So if it is equal to null, any character of a word, then we return false, else we move to that character or we move to the node. So let's say A, B, C is there, and A, E, D is there. So simple like this. This is some type of try, and we have to search for A, E, and F. So we have to search for this. So first we take from root, we take for A, we take for A. Okay, see, here what we do, we take from the root, we check if the children of the root with a value A is equal to null or not. If it is equal to null, then we will return false, else we move to this. We move from here to here. This is our movement from root to A. Then afterwards we check for what? We check for second character E. Does any child of A has E or not? If we have E, then we move to that. Okay, then any child of E, does it have F or not? So there is no child of E that has the value F and that is not equal to null, means there is no node with a value F. So we return false in this case. Now the same thing we would do here. Okay, so first thing what we are doing, so this is so here, since whenever we encounter a dot like this, A dot F, so that means we have to check for A, B, this subtree and also this subtree, because in this type of situation, A dot F, we have to check for all the children of A. Got it? So for that, to do this thing, what we are doing here, we have simply written a recursive code. Why recursive code? Because in recursion, what we do, we simply do the same thing repeated times, the same thing for multiple times. And for the same thing, what is the same thing here? We have to check for does the a dot f is present or not in all the children of a whenever we encounter a dot. So whenever we encounter a dot, we will do a recursive solution that we will call the function again, simply because we have to check for all the children of a, and one way to do this is by using recursion. So yeah, this is the base condition. If index equal to word dot length, so there is no characters present here, then we have to check does the current is the end of the word or not. If it is the end of the word, we will return true or false. Okay, now we take the character at the current index, and we check if the character is dot or not. So if a character is dot, then as I said you earlier, then whenever we encounter a dot, we traverse through all the children of the current node. See here, we will traverse to all the children of the current node, and if the child is not equal to null, and in that case we will again call the search helper function. Okay, so here in this case we are at a. Now at a, after a, we encounter a dot. So whenever we encounter a dot, we will take a look for all the children of a. We will travel for all the children of a that is not equal to null. This is first condition. So here we will check for child B and child C. We will check for these two child because they both are not null, and we again call this helper function. So for dot we will check for a, b, and further, and a, e, and further. Okay, and if a character is not dot, so let's say that afterwards we will check for f. F is not a dot. So in that case, we will simply check this thing. We will simply check this, that if the current pointer has a children whose value equal to f and that is not null, okay, then we will return true. In that case, we will return true if that is the end of the word. Okay, correct. So the last has to be end of the word. So the base condition is that only. So yeah, that's why if it is a null pointer, then we will directly return false as we are doing here. And if in the else if it is not a null, then we again call this search helper function, because our base condition is that in the search helper function, right? So yeah, we will check after dot, we will check for both the substring, and we will see if f is present. So no, f is not present, so we will directly return false here. Got it? So yeah, I hope you guys understood the solution. It is very much similar to the trie data structure. The only thing we are doing here is whenever we encounter a dot, we will check for all the children of the current pointer. And the thing is that we are implementing this by using a recursive solution. We are calling this function again, right, with a base condition if there are no characters and the last pointer is the end of the word or not. So yeah, I hope you guys understood the solution. The time and space complexity here would be the same as trie. The only difference here is whenever we encounter the dot, we check for 26 children. So that means our space complexity would be what? See, there are n number of words. M is the maximum length of word into 26. So into 26 is the more multiplication we are doing in the space complexity, because whenever we encounter a dot, this will run for all the children. Because a node in a trie has 26 children. But from the 26 children, we will only make a recursive call for a children that is not null. Correct? So yeah, the overall time complexity for this solution would be this. The space complexity would be this, and the time complexity here would be also big of n into m in the worst case. So yeah, I hope you guys understood the solution for this question. And if you guys have still any doubts, then do let me in the comment section. Make sure you like this video and subscribe to our channel. Thank you.